Okay, good evening, students. In the previous three classes, we have been discussing about the approximate method. We started with the Rayleigh's quotient and then the extension of that Rayleigh-Ritz method. The Rayleigh-Ritz method, we could able to find out not only the fundamental natural frequency, but also depending upon number of functions we choose, either is a comparison function or the admissible function, we can able to find out more and more number of natural frequency and the corresponding mode shape also. And the fundamental premise of these methods are, especially when we are talking about for the they discretize the continuous system to n number of degree of freedom, and then once we discretize it, the eigenvalue problem solution is similar to what is there for the discrete system. And once we get the eigenvalue and eigenvector, eigenvalue can be used for obtaining the natural frequency. And eigenvector, when we substitute back in the series form of the assumed solution, then that gives us the so-called eigenfunction or the mode shape of the continuous system. So depending upon the coordinate, if it is one-dimensional, if we put the x coordinate, we can able to get the displacement, relative displacements of the beam at various axial location. And in the previous lecture, I showed one example also, in which we plotted the mode shape or the eigenfunction, and for first mode and second mode. So that is so now today also we will be exploring a new approximate method, which is very identical to what we have been discussing in the last class, but with some slight difference in that. So today we will discuss a method that is called assume mode method, and we will be having two more methods to discuss. That is, one is a Galerkin method. Those who are doing the finite element course, they must have been exposed on this Galerkin method. And then lastly, we'll discuss another method that is called collocation method. And that is the easiest method among all, but there is some associated difficulty in the eigenvalue problem of that method, because the eigenvalue matrices becomes asymmetric. So the eigenvalue problems solution is more difficult there. So I will share my slide for today's lecture. Yeah. So this assume mode method, the main difficulty when we talk about the Rayleigh-Ritz method is that we need to choose the comparison function. We discussed something about the Rayleigh-Ritz method, re-examination of the boundary condition. And in that case, we could able to choose the instead of comparison function, admissible function, in which we have less requirement. So this assume mode method is based on the choosing a linear combination of admissible function to start with. So this is the assumed solution, and this is the admissible function multiplied by the generalized coordinate. So in the Rayleigh-Ritz method, generally we used to multiply this function with the constant, But in the assume out method, the main difference is that we multiply with the time-dependent generalized coordinate multiplied by this admissible function. So here there is no requirement of the comparison function to start with. In the previous lectures, we have seen that how we could able to convert the continuous system to discrete system, especially when we talk about energy. In the discrete system, we have been deriving the kinetic energy and potential energy in this series form, in which these are the generalized coordinate and this is the mass coefficient. And similarly, when we talk about and this mass coefficient here will be expressed in terms of that admissible function or in the form of integration or whatever we'll see in the subsequent slide. Similarly, for the potential energy, when we get the potential energy in the discrete formulation, we get this form of the potential energy where Kij is the stiffness coefficient and these are the generalized coordinate. Here is stiffness coefficient again will depend upon the admissible function which we have chosen, because here we are talking about basically the continuous system, but this has been discretized to n degree of freedom system. So obviously our coefficients, the mass coefficient and stiffness coefficient, will depend upon the assumed admissible function. And earlier we have seen that when we substitute this kinetic energy and potential energy in the Lagrange's equation, we get this kind of the linear equations. These are the equation of motions in which mass coefficient and stiffness coefficients are appearing, and these can be there are any number such equations, and they can be when we want to convert into for free vibration, the eigenvalue problem formulation becomes like this, where this inverted V is nothing but the frequency square. Inverted V we are using because here we are seeking the solution which is approximate. Actually, it is a continuous system. We discretize it. So in the discretization, we got the approximation. And so that's why instead of lambda, we are writing just inverted V, just to distinguish that this eigenvalue problem is approximate in nature. And these expressions can be written in the matrix form. Earlier also we wrote the matrix form, the eigenvalue problem for the discrete system. So here, once we get the eigenvalue, that will be the natural frequency. Eigenvector, we need to substitute back in the chosen series form of the function to get the eigenfunction or the mode shape of the actual continuous system. So here, because actually the system is continuous, even we have solved the eigenvalue problem the discrete way, but we need to come back to the continuous system, the relative displacement. So this is the relative displacement which we will be giving at different axial position of the beam. So here this particular method, the assume mode method, is because we have a continuous system. In continuous system, we can have some discrete disks or springs. So those things also we can able to incorporate in this particular formulation without any issue. In the previous lecture, we already seen when there are discrete disks and springs are there, then we can able to include that in the kinetic energy and potential energy, and then we can get back the stiffness coefficient and mass coefficient in terms of not only the continuous part but also the discrete disks and the springs in the system. So now I'll take up, so method is very simple. Now I'll take up one example. So this particular example is a simply supported beam. I'm discussing about the transverse vibration of beam. That is very important to note that once I'm saying transverse vibration, the L operator, M operator will be different. If I'm taking the same beam, but if you want to analyze the axial vibration, then the L operator and M operator will change. Accordingly, our equation or the stiffness coefficient, mass coefficient will be having different uh, form. So here the mass distribution is given. Right? So it is not a uniform beam actually. This is just a representation of a beam, but the beam mass is varying like this. The property of the elastic property of the beam is also having some distribution. Here we are using the assumed mode method, and directly we'll be using the admissible function. And here I'll take two cases. One is I'll take one admissible function in the series form. Then I'll take two, so that once I'm taking two terms admissible function, then I'll get two natural frequency. But if I'm taking only one, then I'll get only one natural frequency. So just for comparison, if we take more and more term, how our natural frequency is getting estimated more accurately, that I want to illustrate in this example. So these are the given thing. So as I was telling, the L operator and M operator will be different for the beam case. So this is given to us. So coming to the boundary condition, because we need to choose the admissible function which should satisfy the geometrical boundary condition of the problem, not the natural boundary condition. So here you can see at x is equal to 0, we have displacement is 0 and bending moment is 0. Similarly, at x is equal to L, we'll be having displacement 0 and bending moment 0. But here requirement is that while we choose the admissible function, only the geometrical boundary condition we need to satisfy. We are not bothered about this. So this is one of the admissible function, x into x minus L. So you can able to see that if I put x is equal to 0 in this function, this becomes 0. So it is satisfying the first geometrical boundary condition. Similarly, if I put x is equal to L here, then also is becoming 0. So this is satisfying the second geometrical boundary condition also. Another constraint is that it should be differentiable up to p times. Here in our L operator, the fourth degree differentiation is there. So 2p is equal to 4. So p is equal to 2 is there. So that means this function which we have chosen, we should be able to differentiate twice without vanishing this term. So if we take the differentiation of this once, I'll get 2x minus L. If I take another time differentiation, then it becomes 2. So it's not vanishing, this is not becoming 0. So it is satisfying the admissible function requirement that it should satisfy the geometrical boundary condition and it should be differentiable up to the p times. So now we have checked the admissible function requirement of the chosen function. Now we'll go for the formulation of the stiffness and mass coefficient as we did in the previous class also. So this is the Rayleigh's ratio, Rayleigh's quotient, and this is the potential energy, this is the kinetic energy star part. And because our assumed solution is in the series form, so this ux we are replacing by the w, and because this is a second derivative with respect to x is there, so this is double prime is representing the differentiation with respect to x twice. There is no differentiation in the denominator part. So now we'll substitute this series form of the solution. So I'm deriving the general expressions that can be used for n is equal to 1 also, and n is equal to 2, or any number of n's. So once I substitute this, because this is square term is there, so I'm taking two dummy variable I and j, so that we'll get the proper multiplications of these. And here double primes are there in the denominator. Again, because this is square term, so dummy variable I and j is there. Now what I'll do, I'll bring the summation outside the integral, and all the terms which are constant I'll take out from the integral. So this similar I think is exercise we did in the previous class also. So now you can see that brought the summation outside, and also the constant outside the integral. And now this expression within the bracket I'm representing as Kij, and this term is Mij. So these are the coefficients, required coefficient, stiffness and mass coefficients, which we need to calculate. Here we have double derivative of the admissible function. So you can see that why we insist that the admissible function should have the second derivative. If this is not second derivative, or term is, if it is vanishing, this stiffness coefficient will not contribute anything. That will become 0. So that's why we have the requirement that the admissible function should have the differentiation up to second order, should not vanish. In mass coefficient, there is no differentiation required, so there is no issue. Now coming to our admissible function, we'll substitute in the because we are second derivative. So once we take the derivative of the admissible function twice, we already seen that is 2. Now we want to calculate the K11. So K11, so we'll put I and j is equal to 1, 1. So this is the K11 coefficient, stiffness coefficient. Here now this EI is function of x, which is given in the problem that the property of the system is varying like this. So we need to substitute this function instead of the EI. So EI naught by 3, and this is that particular function which is given to us. Then the differentiation of this, we already got 2, because they are same terms, so square of that is here. So here now we need to integrate this with respect to x, and then put the limit 0 to L. So after doing this, we'll get this K11 as 4 EI not L. Similarly, we can do the M11. Here we have there's no derivative, but M is having variation. So M is having this kind of variation similar to the EI, and function which we have chosen, admissible function, is square of that, because here both the terms are same. So square of that. Now here we need to do expansion of this, then multiplication of this, then integration of this. So after doing that, we will get the mass coefficient like this. Now once we have mass coefficient 1, 1 and K11 stiffness coefficient is there, we can obtain the natural frequency of the system, fundamental natural frequency, that will be given by K11 by M11. So if we substitute these here, we will get the natural frequency is 10 and on something like that. This. So we got the natural frequency. The eigenfunction or the mode shape will be given by the chosen admissible function. So admissible function is x into x minus L, and multiplied by a constant, because the shape function is always relative. So this constant will be arbitrary. If we normalize, then this constant will have some specific value. Otherwise, this is a relative value, so it's having no meaning. So we could able to get the eigenfunction. So here you can see if we put the x is equal to some value, we can able to see how this particular function will vary over the beam length. So that will be representing the mode shape corresponding to this natural frequency. So this is simple. We have chosen only one admissible function. So we had only single natural frequency we got. Now we'll go for the two comparison functions or the admissible function. This should be admissible function. So x square x minus L. So if you see, this is satisfying both the geometrical boundary condition as we checked earlier, because here we have just put instead of x square. So this will satisfy at x is equal to 0 also and x is equal to L. So geometrical boundary condition it will satisfy. Differentiation, anyway, there is a higher order polynomial. So it will be differentiable up to the second thing. So if we differentiate, we are not getting the 0 value here. So that is fine. So now we have satisfied the admissible. This is admissible function. Admissible function requirement we have checked. Now, however, solution will be like this. So here we'll be having A151 plus A252 because there are two terms we are taking. So the shape function or the eigenfunction will be having A151 plus A252 form. Now, because we have already we obtained earlier the how to get the K11, K12. So here K11 is exactly same. There is no change as we calculated earlier. K12 in the obtained expression, if we put I and j as 1 and 2 respectively, we'll get the K12 expression like this. So here phi1 double prime and phi2 double prime. So here anyway phi1 was I think only, so first one is the EI. EI is this term. Phi1 double prime was only 2. Phi2 double prime we obtained, that is was 6x minus 2l. In the previous slide we obtained 6x minus 2l is the phi2 double prime. So now we need to multiply this and then integrate and put the limit. Then we'll find that K12 will be this. Similarly, K22 will be the EIX. Here both I and j are 2, so this will be phi2 double prime. So here this is the EI variation, and because there are two terms, so square of that 6x minus 12 square. Again here we have to do long integration and then put the limit to get the final K22 value. So we have obtained the stiffness coefficient K11, K12, and we know that symmetry is there. So K21 is also known to us. K22 is this. So the stiffness matrix 2 by 2 is not, now we know. Similarly, now we can obtain this mass coefficient. So mass coefficient is this from the previous exercise. Then M12, just we need to change this eigenfunction. So this is the phi1 and this is the phi2. Again integrate it, so we'll get the M12. M21 also will be same. M22, then we need to take the phi2 square. This is the phi2 square term. So here we have taken the functions in the polynomial form. So integration is relatively easier. Sometimes if we take the sine function, cosine function, then that becomes more difficult. So we could able to get the M22. So now we got the mass matrix also 2 by 2. So now this is the mass matrix we got. This is the stiffness matrix we got. Now you can see that these are the discretized mass and stiffness matrix for a continuous beam having varying mass distribution, varying elasticity distribution. Exact eigenvalue problem formulation will be very difficult for such case. Those already who have started attempting the assignments, they must be feeling the difficulty of that using continuous system approach, how difficult the equations becomes. But here we are not solving any differential equation. Just by integrations of some polynomials, we could able to discretize the continuous system having complex geometry to 2 degree of freedom system. So now we have mass and stiffness matrix. We can go for the eigenvalue problem as we had for the discrete system. We have been doing for discrete system from very beginning of the class. So eigenvalue we can able to obtain. So that will give the natural frequency. So this is the first natural frequency which we'll get from the eigenvalue problem. Corresponding eigenvector we can get. So this is the eigenvector corresponding to the first natural frequency. This 2 is representing that we have taken 2 terms in our eigenfunction, and NF1 is the first natural frequency. This is the corresponding eigenvector. Here eigenvector is those terms which we multiplied with the admissible functions. So now you can see that the whatever we have chosen earlier eigenfunction. So this is the admissible function, second admissible function multiplied by the generalized coordinate. So we need to substitute this vector which we obtained here. A1 will be 1, A2 will be 0. So and U1 is the first eigenfunction, the admissible function is the second admissible function. So 0 is here. So that means here only the first term is coming. This term is coming. Similarly, this is the second natural frequency from the eigenvalue problem. So, and this is the corresponding eigenvector. So, eigenvector is this. Now, if you want to get the mode shape, we need to substitute in this. A1 is this minus 0.5L. This is first admissible function. A2 is this one, 1. And this is the second admissible function. So, now we could able to get 2 natural frequency and corresponding mode shape. Now we'll plot this. So this is the first eigenfunction which we obtain. So if we plot this from 0 to L, this is the half sine wave. We know that for cantilever beam, for simply supported beam, we get the half sine wave of the corresponding to the fundamental natural frequency. Similarly, this is the second eigenfunction corresponding to the second natural frequency, and this is full sine wave. So there is a node here. So this is nothing but the plot of this function which we obtain after substituting the eigenvector here. Now if you want to compare, so this comparison I will come back again. Actually, this is the natural frequency we obtain. This is the natural frequency we obtain if we take the comparison function instead of the admissible function, because we know that comparison function is having higher requirement. But if we can get the comparison function for simply supported beam, and if you use it, we are expected to get the better natural frequency. So next I will be just showing that particular example in which I have taken the comparison function and we got these natural frequencies, and you can see that they are lower than this. So generally when we are taking more terms, then we get the lower value of the natural frequency, and lower that means is going more closer to the actual ones. So because we already know that the Rayleigh's quotient gives the upper bound to the lowest natural frequency. So so this particular comparison function is predicting the better natural frequency. I will show that particular exercise. Just I will show. So this is actually the code, MATLAB code, but the same can be changed to the Scilab by changing here and there some small variations. So you have observed that a lot of integrations are involved, symbolic integrations. So this particular code can do all those integrations directly, and even it can plot the mode shape. So here you can see that these are the symbolic variables which we'll be using. So the x is the displacement location, mass, length, Young's modulus, I. These are the symbolic variables. We know the distribution of the mass is given in terms of x, L, like this. Similarly, if the elasticity is given, we have chosen one admissible function like this. So if you're choosing any other admissible function, you need to change here on. This is the second admissible function. So initially, I have solved for the first natural frequency by choosing only the U1. So you can see that we require the second differentiation of the admissible function. So this command gives that. This is the second differentiation of the second admissible function. Differentiation of the second admissible function. K11 we can able to calculate. You can see this EIX, second differentiation of the U1 and square. So we had the phi 1 double prime square. So this is that particular term, x varying from 0 to L integration. So directly we can able to integrate that function here using k. We can get the k11, similarly m11, and natural frequency we can obtain by square root of the k11 by m11. Similarly, we can go for two admissible function. We can obtain k12, k22, so we can get the stiffness matrix. Similarly, the mass matrix can be obtained. Directly symbolically, it will integrate and display. Then we can even solve the eigenvalue problem. We can get the mode, the eigenfunction, eigenvalues, eigenvector. Then we can plot. So this is the plotting of the eigenfunction. So this is in assignments. If you want to use this, you can use it, or if you want to do by hand calculation, that is also welcome. So the same problem I have here shown if we use the comparison function. So as we know that if we use the the exact natural frequency, if we use the comparison function, we'll get the less accurate as compared to the eigenfunction. But if we use the admissible function, then further less accurate natural frequency will get. So here, because these boundary conditions were simple, so I could able to choose some comparison function, and I'm just showing the basic steps which are there. So this is one of the comparison function. So comparison function, we know the requirement is more stringent. So what is the requirement? That it should satisfy all four boundary conditions. So this particular function, we can check that x is equal to 0, this becomes 0. It requires double derivative. So this is the double derivative of this. So now you can see if we put x is equal to 0 here, this becomes 0. So this is satisfying the second boundary condition, which is natural boundary condition. This x is equal to L. If you put L here, you'll see that is 1 by 12 minus 1 by 6 plus 1 by 12. So this becomes 0. Similarly, this here, if you put L is x is equal to L, this becomes 0. So you can see that this particular function is a comparison function which is satisfying not only the geometrical boundary condition but also the natural boundary condition. So this we can substitute. So this is same expressions. So because there is no change in this, only the k11, km11 we can able to obtain. Only thing we need to use now the new function which we have chosen. In the this expression there is no change. Only thing the functions are getting changed. So we got this, and so we got 9.8. Earlier with the admissible function we got 10 point something. So this is lesser. So we expect this is the more accurate as compared to the previous one. And this is the corresponding eigenfunction, because now this is the comparison function multiplied by that. So because there is only one function we have chosen. Now I'll take two functions, two comparison functions. So this is another comparison function. The previous one was x raised to 4 something. Now there is another comparison function, and you can check that it will also satisfy both the geometrical conditions and the natural boundary condition. So now we'll calculate k11, k12, k1, k12 and k21 will be similar, k22 using new functions. Similarly, the mass coefficient m11, m12, m22. So this will give us the mass matrix and the stiffness matrix. These are the new mass matrix and stiffness matrix corresponding to the new comparison function chosen. And if you solve the eigenvalue problem of this again, we are getting one natural frequency, this corresponding mode shape or corresponding eigenvector here, and this is the eigenfunction corresponding to that, because 1 and 0, so this term will be 0, so only u1 will be there. Similarly, the second mode, this is the second natural frequency corresponding eigenvector we got. This we are getting from the solving this eigenvector 2 by 2 matrix. So here again, if you put the u1 and u2 comparison functions, so we'll get this. So this again can be plotted as we did earlier. So this is the first mode, this is the second mode, and these are the natural frequency, and we compare this natural frequency with the previous one in the previous plot, and both of the present ones are lower than the previous one. So we expect that they are more accurate as compared to the previous ones. So this example gives how we can able to obtain, if we could find three terms in the series of the assumed function, then we could have got three natural frequency. And generally the tendency is obtaining the three natural frequency, the lowest will be further accurate, second will be again more accurate than the this one. So that is the generally the trend we'll find, that as we'll take more and more terms, we will be getting the more accurate lower natural frequencies. This is the corresponding plot or the program, just the change is here. There's nothing change anywhere. So just we are changing the eigenfunction, this function as the comparison function here, and we are getting the all the calculations plots. So this is the output. So this is anyway you can able to check it. So these are the output of various steps. Whatever the differentiation integrations are done, various steps are given. So if you have any questions on this, then I can attend. If you have any questions on this. You can raise the hand in case you have any questions on the method, the example, because you'll be solving the assignments. So you may so so I'll explain the second method. This is so method I will explain. Maybe the example I can take in the next class. So Galerkin method is based on the equation of motion. Those who have done they are doing the FEM course, they know that Galerkin method, the procedure. So here we have the eigenvalue problem. This is the standard eigenvalue problem, the general L operator, M operator, and we are assuming that they are self-adjoint operator and all those things. And this W is subjected to both geometrical and natural boundary conditions. So here the assumed solution should have the comparison function. In the Galerkin method, if you're using the functions which we choose should be comparison function because it's based on the equation of motions. We have seen when we have the energy form, then the requirement of the this comparison function can be relaxed. But in the Galerkin method, because the starting point is equation of motion, so when we choose the assumed solution, that should be comparison function only. And AI is the coefficient which we need to find out to minimize something. So that means this is the assumed solution, which is approximate in nature, because in a continuous system we should have infinite number of terms, but we have truncate up to the n. So now if you substitute this here, this equation will not satisfy completely. So in this equation, if we bring this mass term here and we represent this as a function, so if we substitute the approximate solution here, we will not able to satisfy completely because this is approximate solution. So we'll get some error. So epsilon is a error because of the approximate solution. Now also the lambda we have replaced, earlier it was lambda, that n will be replaced by inverted v, and that is representing that because the this is approximate, so this is also whatever the eigenvalue we'll get from this will be approximate. So this particular error we are multiplying by some weight and we are integrating over the domain. This weights in the Galerkin method is same as the whatever the comparison function we are choosing. So basically we are minimizing this particular error, and here we know that the assumed solution is having some unknown constant. So this unknown constant to be found out such that the error get minimized. This error get minimized over the domain. So if you substitute the error function here, so we'll get this the error multiplied by this function, comparison function. Now if we expand this bracket, if we open the bracket, then this will get two terms, and we are representing this in one. This is one term and this is another term which I am writing here again. So this particular term of the left side, this term is being taken, the left side one. Now Wn is in the series form. Okay, if you go back here, the Wn is in the series form. You again go back here, Wn is in the series form. So if you put some Wn here, I was just Wn here. So and because in summation I have changed the integration and the summation order, and I've kept the constant outside the integral. So if I substitute Wn here, I'll get expression like this, and this expression I am representing as KRJ, or subscript for the weight function and J for the inner one, KRJ. So KRJ or KJR, they are symmetric and can be expressed in this form. So now we can see the difference of the KRIJ which we represented earlier, and here we have the L operator with this. Earlier it was second derivative or the beam case. So, but here for the beam case we'll be having fourth order differentiation. So that's why the requirement of the comparison function is there, because L is fourth order differentiation for the beam case. So this chosen function cannot be admissible function, otherwise this will become 0. Similarly, if we take the other part of this one, we substitute W in the series form, and then again interchange this integration and summation, will get NRJ like this. So NRJ is this, and if we substitute, again go back to this equation, we substitute this Kij, Mij, or Mi, MRK, MRJ, and KRJ. So this is a simultaneous equation. Again, that can be written in the form of matrix like this, which is a discretized form of the eigenvalue problem from the continuous system having n degree of freedom system. So once we have this, the procedure is same, because then again eigenvector we need to obtain, eigenvalue we need to obtain, substitute back in the assumed series form to get the eigenfunction. So here is for this particular case, beam case, binding of beam vibration case, how the K function and the M coefficients will take the form I am showing here. So this for transverse vibration of beam. Okay, so for axial vibration that will be different, torsional vibration that will be different, but here I am explaining for the transverse vibration or the bending vibration. So L and M operators are given by this for the bending vibration, having fourth order differentiation. Now KRJ we obtain using Galerkin method like this. So now we can put the L operator here. So we got this form of the stiffness coefficient. So KRJ will be like this. So whatever the comparison function we have assumed, we need to substitute here, differentiate, and then we need to get all the terms corresponding to the n by n matrix. If we are taking two comparison function, then this will be 2 by 2 matrix, or 3, then 3 by 3 matrix. So in general, this will be n by n matrix. Here, yeah, even we can do the integration by part of this, and this is 2 times integration by part have been done here. So this is the first part, then integration of the second limit, then second time differentiation of the first part, integration of this second time, then differentiation of this again, this one. So this is a integration by part twice. Similarly, the mass coefficient can be obtained like this. So generally, we'll be having this form of the for calculating the stiffness coefficient and mass coefficient. So this maybe I will take up another example of the same example, how we can able to obtain the using this Galerkin method, the matrix and other things, and we'll compare that with the previous assumed mode method. So I have taken the same example for this also, so that we can compare, okay, the results. So, if you have any questions, you are welcome. So again, I will advise that please attend the assignments, because I've given very few number of assignments, but if you complete that, I think then only you can able to understand the subject very well. Because in the exams, we are not able to take the, the larger derivations, and if you solve these assignments, I think your concepts will be clear, and that will be helpful for your other if you're doing MTP or other things in similar subjects. So, and several people are also asking questions, doubts. So that is, so unless you do these assignments, you will not have any doubts. So, so encourage you attempt, and any difficulty you show the in snapshot of whatever your derivation you have done. Ask the question key if you're facing some difficulty somewhere, so that I can I can know where is you are facing the difficulty, and I can give some suggestions on that. So if there is no question, then I'll stop here. Okay, goodbye.